Hello everyone, I'm Theo and on behalf of Group 12 would like to welcome you today and thank Imperial College for giving us this opportunity to present to you a real world case on wind energy curtailment analysis in Orkney Islands. The data is from wind turbines, and the aim, apart from blowing in the wind, is to examine the relative value of a demand response energy scheme in Orkney Islands. Our main hypothesis is that by controlling energy demand, especially when there is excess supply availability, a better stabilized energy grid could be preserved. We have focused on valuing the cost of curtailment and market sizing the Orkney's energy consumption market. How much is the energy demand side and how much could this potentially be reduced by DR penetration, and how many local households will need to be on DR scheme in order to supply this level of DR?
Okay, thanks Theo. I'm going to talk to you about wind energy capture and wind simulation. So let's start first by looking at the top graph here in blue. This is illustrating the data that we received from the turbine, which had, for many records, perhaps every minute, corresponding prevailing wind speed and power output of the turbine. You can see, whilst there's a reasonable spread, there is a high concentration of points on the left-hand side of the chart, starting from about 5 meters per second, where the turbine starts to produce power, increasing to 900 kilowatts at approximately 12 meters per second, and then falling off again at around 30, where the wind turbine would be typically taken out of service to avoid damage from strong winds. So fundamental is being able to fit this power curve. We've proposed 3 approaches: a polynomial fit, which is quick and easy but has some undesirable oscillations, interpolation with univariate spline, and lastly a parametric fit. And we've actually chosen to proceed with the parametric fit because it's very fast and it gives us a very easy to understand data set, and we could use it for other turbines rated at different levels without necessarily having a need for observable data. Now if we move on to look at wind simulation, we have the case where we know for the one location from our data what the wind mean speed and standard deviation is. We can back that out of the data. But if we're having multiple locations, we don't have that data. So we want to be able to produce hypothetical simulations. So taking the mean and standard deviation to be consistent in 2 locations, but being able to introduce a correlation we achieve through applying a copula function. You can see in the bottom left, with a high correlation, the wind speed at the 2 locations is very similar. But when we run with a lower correlation, we have a high degree of dispersion. So this allows us, for a specified mean and standard deviation at locations and an indicated correlation, to be able to hypothesize the power production capability of the wind farm.
Calculate the curtailment and try to prove our hypothesis, we used 5-time series of data, historical data, which we're illustrating here for a sample week in March 2017. We looked at the set point in kilowatt. There is the cap of the turbine in comparison to the actual power that was produced by the turbine in blue in the first swim lane. We then looked at what was the wind speed in milliseconds at the point in time of the different power that was produced, to then work out what we could have actually produced using the models that we presented earlier. In parallel, we also used the customer demand data, or the household demand for the given timings, to try to understand what type of DR we could do to reduce curtailment. And you notice here how even day by day we see an interesting pattern of the demand, which is probably associated with different hours of the day. And finally, we loaded the pricing of energy, historical pricing of energy at the given points in time, so that we can work out what the revenue that we lost by curtailing energy. So speaking of curtailment, we want to quickly clarify what we defined and used as curtailment. In a nutshell, curtailment was pinpointed at the times when the power was pretty much overlapping with the set point, and also when we found that the power was lower than the maximum power that could have been produced given the average wind speed at the time. To look at the energy curtailed and work out its value, when we determine the actual maximum power based on wind speed, and we're showing it here in orange in the stack bar by month, we found that the maximum power is actually quite close to the actual power that was produced, and this led us to believe that we're probably not curtailing that much, and we are probably not going to see a large monetary benefit from reducing this curtailment. But let's see if our intuition was right. We present you our results for 2 years, where 2016 and 2017, where in blue we have the curtailment and in green we have the potential revenue. So if we take the year of 2016, we see that there was up to 205,000 kilowatt hour energy curtailed for that year, and that would equate to a corresponding £10,000 roughly potential revenue that was lost because of the curtailment. If we think that if we make the assumptions that we have 21 turbines in Orkney, and that assumption is made based off us looking on Google Maps essentially, that leads us to a potential revenue or revenue loss of £210,000 per year, which in our view is not hugely significant. If we try to look specifically at what times of the year the energy is curtailed, it's not surprising that we have the longer lines or the highest curtailments in Q3 and Q4 of the given years, and correspondingly the higher potential for revenue. So should we choose to engage in DR, we may want to target the periods of the year with the highest curtailment.
This chart illustrates the monthly ratio of power production to demand over 2017, both in terms of actual production and in terms of the maximum that could be produced given actual point-in-time wind speeds and the turbine's maximum capacity. It assumes there are a total of 21 turbines in Orkney and that all of them have the same capacity. Since production is multiples larger than demand, there is evidently potential for exporting surplus supply. This next chart gives us a more granular view of what's happening with demand for power versus production, showing minute-by-minute power over a period of 4 weeks towards the end of 2017. Production capacity far exceeds demand, which oscillates in a regular fashion according to time of day. Curtailment can be completely reduced, i.e. completely done away with, since the excess power can be exported down the connector since it has a 40 megawatt capacity, which is clearly way above the power that is surplus to demand. Now, if we estimate household energy consumption to be 4.8 kilowatt hours per day, this is approximately 1800 kilowatt hours per year. If we assume 25% of this could be demand controlled, this gives us 1.2 kilowatt hours. Now, given that we found average daily curtailment to be 1000 kilowatt hours, this amount divided by 1.2 kilowatt hours gives us around 830 households which would need to be on the scheme to consume the currently curtailed power. Finally, not all of the turbines on Orkney have the same capacity. For example, the Burger Hill turbine has 2.75 megawatts capacity. Since there are around 5,500 households on Orkney, this means just over 6.5 megawatt hours of curtailment could be recovered each day.
So Andy looked at the technical aspect of our analysis and focused on power curves and wind simulations, and that helped us define a maximum energy production for different levels of wind speed. Julia then defined energy curtailment and quantified the monetary value of the energy lost. Now, we take a look at some recommendations in terms of the implementation of a DR scheme. From Mohammed's analysis, we see that for successful implementation, we need approximately 830 households. Our study also suggests that potential gain from a DR scheme is not uniform throughout the year, and that focus should be towards the end of the year end in quarters 3 and 4. In addition, we see that the potential upside in monetary terms from such scheme does not appear to be amazingly appealing. Therefore, we do not recommend any huge expenditure in the implementation of the program. Finally, we believe that the DR scheme, in order to be successful, customers should be offered discounted energy prices during off-peak hours, which will also normalize the energy usage during the day. And for that, we also recommend installation of smart meters for an effective and transparent communication of pricing to customers. Thank you for your time, and we hope you enjoy our analysis.